Hi friends, welcome to the channel. Today in this video we'll be doing valence shell electron pair repulsion theory, or the famous VSEPR theory. So this theory we use to basically predict the shape and structure or geometry of various molecules. And questions from this part definitely come in all type of entrance exams, let it be JAM, GATE or any other entrance exam that we write. The questions definitely come from this part. And we all have different techniques for doing this VSEPR theory. For predicting the structure, we all use different methods. And just have a look at this method in this video that I use. And using this method, I tell you, you can solve any molecule. You can find the shape and geometry of any molecule in less than a minute. So moving on to the topic. So to give a brief overview of the topic, so the VSEPR theory, or the valence shell electron pair repulsion theory, it was given in 1957. It was given in 1957 by two people. That is, one is Nyholm and the other person is Gillespie. These are the two people who proposed this theory in 1957 to predict the shape of the molecule, to predict shape and also the bond angle. So, and this theory, as the name suggests, VSEPR, valence shell electron pair repulsion. So this theory we use, or we predict the shape of the molecule and depending on the electron pair repulsion of the electron pairs in the valence shell around the central metal atom. So it is the repulsion that give rise to various shapes or geometries to the different molecules. And the electron pairs that we have, the electron pairs can be of two types. We can have two types of electron pairs. One is, we can say, the bond pairs, and the second type is the lone pairs. These are the two types of electrons pairs that we can have. And what are these bond pairs? Bond pairs are those electron pairs which form the bond between the central metal atom and the surrounding atom. Those bond pairs. And lone pairs are those electrons which are which are localized on the central metal atom. It is not being shared with any other surrounding atom. It lies localized on the central metal atom, and because it is lying localized on the central metal atom, it is not being shared by anything. So this give rise to more repulsion. Lone pairs provide more repulsion. They take up more space. They provide more repulsion compared to the bond pairs. And so you can say that my lone pair repulsion would be greater than lone pair bond pair repulsion, and that would be greater than bond pair repulsion. So if you talk about the repulsion, this is how it would be. Lone pair repulsion would be the most, followed by lone pair bond pair repulsion, and finally bond pair repulsion. And the repulsion between the bond pairs, it depends on another factor, which is the electronegativity difference. We have electronegativity difference between electronegativity difference between the central metal atom and the surrounding atoms. The bond pair repulsion would depend on the electronegativity difference between the central metal atom and its surrounding surrounding atoms. Clear? Now, based on the number of electron pairs, the total number of electron pairs we have, we can have certain geometries for a molecule, and we can have certain shapes. Depending on what is the total number of electron pairs, we can have certain geometries. And when you consider the bond pairs and lone pairs into it, we can have certain shapes also for this. So there's a difference between geometry and shape. So when they say geometry, it means that we consider everything. We look at the total structure, which includes both the bond pairs and the lone pairs, and that's how we say about the geometry of the structure. But if the shape of the structure of the molecule is asked, it means that we don't consider the lone pairs, we only consider the bond pair part of it, and then we predict the shape of it. Now, depending upon the total number of electron pairs, if the total number of electron pairs is 2, then the geometry would be linear. And there is only one possibility of dividing this total number 2 between the bond pair and the lone pair. That is, we can have 2 bond pairs and 0 lone pairs. That's the only possibility. And in that case, we would get a linear shape. And if the total number of electron pairs is 3, if we have a total number of electron pairs to be 3, it means that the geometry of my molecule would be trigonal planar. And this 3, the total number, can be divided between bond pairs and lone pairs in two ways. One is 3 bond pairs and 0 lone pairs, or it can be 2 bond pairs and 1 lone pair. So when I do like that, if it is 3 bond pair and 0 lone pair, then my structure would be trigonal planar. But when I'm having 2 bond pairs and 1 lone pair, then my shape would become in a bend shape. The geometry is still trigonal planar, but when I talk about the shape, this 2 bond pair and 1 lone pair would give rise to a bend shape. Okay, so we have a whole table like that for 2, 3, 4, 5, 6, 7, up to 7. To having total number of lone pairs can be up to 7 number, means we have different geometries, and depending on how we are arranging the number of bond pairs and number of lone pairs, we can have different shapes also. Now we'll go to solve the questions, and for that, let us consider the examples that has appeared in various exams for us for the entrance exam. So I'll take up some questions from there, and using those questions, I'll solve the structure for you using VSEPR theory. So the first molecule is TeF4. It has appeared in JAM 2014 paper. So let's predict the shape and geometry of TeF4 using VSEPR theory. Let us look at the steps involved. So the first step that I do is I have to write down the valence electrons. How many valence electrons does the central metal atom? In this case, it is tellurium, which is my central metal atom. How many valence electrons does tellurium have? Tellurium falls in the oxygen family, oxygen, sulfur, selenium, tellurium, polonium. So it falls in that category. So oxygen family. So tellurium would have a valence electron, six valence electrons. So I have to represent those 6 valence electrons. First step. That's the first step involved. So 1, 2, 3, 4, 5, 6. So I use this cross marks to represent the electrons, valence electrons. So I represented 6 valence electrons. The next step that I have to do is I have around this tellurium, I have fluorine atoms. So there are 4 fluorine atoms around this, and these fluorine atoms, they can share these valence electrons of tellurium. Each fluorine atom would take up or would share one of these valence electrons from tellurium. There are 6 valence electrons, but in each fluorine atom would share one of those valence electrons. So let us mark that. So if we come here, so this first electron would be taken by one fluorine, would be shared. The second electron shared by the next fluorine. My third electron shared by the next fluorine. And the last, fourth electron would be shared by the last fluorine. And now what I have is, I have 2 electrons remaining without being shared. And that will act as my lone pairs. Lone pair means I should have 2 electrons. 2 electrons would together form one pair. Okay. So I have the remaining 2 electrons here. So these remaining 2 electrons that I have here, that is not shared with anything, that would act as my lone pair. So I can say totally in this case, I have 4 bond pairs, that is with the central tellurium. 4 of the fluorine atoms are bonded, giving rise to 4 bond pairs. Apart from that, plus this 2 electrons that are not shared with anything, that would act as one lone pair. And together that would give rise to 5 electron pairs. So totally 5 electron pairs. So from the table we know that if we have 5 electron pairs, then the geometry would be trigonal bipyramidal. So that is, I would have my tellurium, then around it I would be having 5 bonds like this. And out of these 5, this is trigonal bipyramidal. Out of these 5 bonds that I have, these electron pairs, 4 of them are bond pairs and 1 is lone pair. And to avoid repulsion or to have minimum repulsion, the electron pair would be this lone pair would be far away as possible. So this would act as my electron pair. It would stay far away to avoid repulsion, and the bond pairs would be these. So fluorine, fluorine. I have fluorine here and I have fluorine here also. So now if I look, I can find that the shape. When to find the geometry is totally considering the 5 electron pair. My geometry would be trigonal bipyramidal. But coming to the shape of it, I have to ignore those that lone pair. Ignoring the lone pair and considering just the bond pair part, if I look, I can find that the shape looks like a seesaw. So I have a seesaw shape for tellurium tetrafluoride TF4, and I have molecular geometry to be trigonal bipyramidal. Okay, clear. So for this case that I have here, my geometry would be, for this molecule, I can say that my geometry can be written to be trigonal bipyramidal, and shape is given to be seesaw shape. Okay, let's move on to the next question. Next is sulfur trioxide, SO3. So this is NET December 2012 paper. So this is not a complete question. It was only part of the question. They had other molecules also. So out of so many molecules, it asked which of them has a planar shape or something like that was the question. And SO3 was one among the different options given in the question. So I've just taken the SO3 part. Now let us see how we can predict the VSEPR structure for SO3 molecule. So again, the first step is writing the valence electron. Sulfur again falls in the oxygen family, so it has 6 valence electrons. So first step is I represent the valence electrons of sulfur: 1, 2, 3, 4, 5 and 6. Now the difference between the previous one and this one we'll see. Now here what we have to do, the next step is that we have to share, write the sharing of those electrons of valence electron with the surrounding atoms. That is the second step. But the change here is that the previous one was a fluorine, a halogen atom. So halogens are, when we consider, they share single electrons only. They share single electrons, but oxygen, we can share 2 electrons that they form. Oxygens, they form double bonds. Like if you consider CH3 or CH4 and all, that carbon, hydrogen and all is single bonds only. But when you consider, if I consider other examples of like the previous example, TF4 and all, means Ta and fluorine is forming single bonds only by sharing 1 electron. But oxygen, if you consider, like we have carbon dioxide and all, so between the carbon and oxygen, it is double bonds which are formed. Always oxygen would form double bonds. So which means that oxygen at a time would take up 2 bonds. Each oxygen should take up 2 electrons. It should each of the oxygen would form 2 bonds with a central metal atom. So it should take up 2 electrons. It should share 2 electrons at a time. So let us mark that here. So my first oxygen would take up the first 2 electrons. Then my second oxygen would take up the next 2 electrons, and my third oxygen would take up the next 2 electrons. This is the case of oxygen. So if we are having oxygen as my central around as the surrounding atom, then it has to take up 2 electrons at a time. So sulfur had 6 valence electrons, 2 electrons each of the oxygen took up, and there is no electron that is remaining free, which means that there is no lone pairs. This molecule has only bond pairs. It has only 3 bond pairs and 0 lone pairs. So I can write it as, it is 3 bond pairs plus 0 lone pairs. So totally this is 3 electron pairs. So 3 electron pair means I would have my central sulfur atom, and around it each of the oxygen atom would form double bonds like this, oxygen here and this oxygen here. So this is how SO3 would look like, and since it does not have any lone pair, its molecular shape, geometry and the shape of the molecule both would be the same. It's triangular planar, trigonal planar shape and geometry. So both, if I consider the shape and geometry, I can say write the geometry and the shape, both of them would be trigonal planar. Okay. So if it had any lone pairs, then the shape would be different. But since there are no lone pairs here, both geometry and shape are the same. Moving on to the next question. So this is from JAM exam again, JAM 2007 paper, to predict the structure of CH3 minus. Now earlier we saw 2 neutral species. One was of halogen involved species and another one was an oxygen involved species. The surrounding atom was an oxygen. 2 cases we saw for neutral species. Next we are looking at cases of anions where we have negatively charged molecules. How would we use the VSEPR theory to predict the structure? So here central metal atom is carbon. Steps are the same. So carbon is having valency 4 valence electrons. So I represent the 4 valence electrons as always. That's the first step, representing the valence electrons. So here carbon has 4, 1, 2, 3, 4 valence electrons of carbon. And because there's a negative charge would mean an extra electron. A negative charge indicates that we have an extra electron. So I have to add one more electron to this. That is, I add one more electron. So totally 4 from the valence electrons of carbon and 1 extra electron from the negative charge. So totally it is 5 electrons that I have marked. And 3 of the hydrogen atoms, hydrogen would take up 1 electron at a time. So each of the hydrogen would share 1 valence electron. So taking up the first one, so here this would be taken up by one hydrogen, the next one by another hydrogen, and the next one by another hydrogen, and the last 2 electrons, there are no hydrogen or no other surrounding atom to share those electrons, and they are vacant, and those will act as the lone pairs. So then these 2 electrons would together stay as one lone pair. So totally I would have 3 bond pairs plus 1 lone pair, and that would give rise to 4 electron pairs. 4 electron pair if I'm having, the geometry would be tetrahedral. Tetrahedral would be the geometry. So I have my carbon here. So I should be having 1, 2, 3, 4. Now out of this 4, only 3 of them would be the bond pairs, and the last one, which is far away, the far apart one, would be the lone pair. Lone pair would stay away from the bond pairs because of lone pair, bond pair repulsion is high, so they will stay away. They would stay far away. So lone pair would be on top, and the 3 bond pairs, they would be staying the down. This would be the tetrahedral geometry, and we'll be having a trigonal pyramidal shape. So in this case, I can say my geometry can be tetrahedral and shape can be pyramidal. Okay. Let's consider the example of a cation, a positively charged molecule. We have ClF4 plus here. This is from GATE 2009 paper. So the steps are the same. So first we have to write the valence electrons. So we have to represent the valence electrons of the central metal atom. So in this case, my central metal atom is chlorine. Now the difference is that since I have a positive charge, out of the 7 valence electrons of chlorine, one of the valence electron would be missing. A positive charge would mean that it's a loss of an electron, and a negative charge would mean a gain of an electron. So here, since I'm having a positive charge, chlorine is having 7 valence electrons, but out of those 7 valence electrons, one of the electron would be missing, and I would have to represent only 6 of them. So let me represent the 6 valence electrons of chlorine as 1, 2, 3, 4, 5, 6. And now I have to represent the bonds. Each of it would be shared by 1 fluorine atoms like this. First fluorine, second fluorine, third fluorine, and the fourth fluorine would take. And the last 2 electrons that I have, that would act as a pair of lone pairs. That would pair up together as 1 lone pair. So totally I'm having 4 bond pair plus 1 lone pair. So which means it is equal to 5 electron pairs. So 5 electron pair means I can write it as chlorine here 1, 2, 3, 4 and 5, and the fifth one would be the electron pair here, far away one, and the other ones would be the bond pairs, and the fifth one was the lone pair. So here my geometry is trigonal bipyramidal because the value is 5 electron pairs. So it has a trigonal bipyramidal geometry. But coming to the shape of it, because of 1 lone pair, the shape of it is, shape would be seesaw shape. So we just have to know the table, and from the table, depending on using the steps, we can find out the number of bond pairs and number of lone pairs and total number of electron pairs. And using that, we can find out the what is the geometry of my molecule and what is the shape of my molecule. VSEPR theory can also be used to predict the bond angles of the molecules. And look at this table. This table is taken from Inorganic Chemistry book by Meisler and Tar. And here the first column is the steric number, and steric number represents the total number of electron pairs. That is both the number of bond pairs plus the number of lone pairs. That is the steric number that is given here. Corresponding to each steric number, their geometries are given, and corresponding to each geometry, we have a particular bond angle also, and examples of each geometry is also given. So here in this table, they've not considered the lone pairs, those involving only bond pairs. Those molecules which involve only the bond pairs are taken. So if you look at the examples, you can see none of those examples have lone pairs. So what happens if lone pair is also there? How will the bond angle vary? We'll study that later on. Now just look at the bond pairs along. When we have just bond pairs in molecules and corresponding to each of the number, we have each of geometry, we have a bond angle. Now, see, the first case is carbon dioxide. Here we can say that this bond angle, linear molecule. Carbon dioxide is a linear molecule. It has a bond angle 180 degree. When I take SO3, SO3 was one of the examples that we solved earlier. So here we can see that this bond angle is found to be 120 degree. It has a triangular planar structure, and so on. We can find for each of the geometries. And now let's see what happens if we have lone pairs also to it, and also we'll look at the contribution of electronegativity of central metal atom. How is that contributing to the bond angle, and also how the lone pairs are affecting the bond angle. Okay, so let's just take this question here. Let's arrange these molecules given here in the increasing order of their bond angle. We have ammonia, H2S, H2O, and methane. First step, we have to write their use VSEPR theory and predict their structures. Then molecular geometries and shapes will be predict for each of it. We'll start from ammonia. Ammonia is my first one. So let me write for ammonia. Ammonia, nitrogen is a central metal atom. Nitrogen has 5 valence electrons. 1, 2, 3, 4, 5. I write that. And these hydrogen atoms, 3 of the hydrogen atoms would share these valence electrons like this, and the last 2 of them would pair up together and they would exist like this. So totally I will be having 3 bond pair plus 1 lone pair, which means it is totally 4 electron pairs. 4 electron pair means I can represent it like 1, 2, 3, 4, 5, like it's a tetrahedral geometry, but because one is lone pair, the top one would be a lone pair, the others would be hydrogen, hydrogen, and hydrogen. This is ammonia. It's having a pyramidal shape. Now coming to H2S, let us look the case of H2S here. H2S means sulfur is the central metal atom. Sulfur has 6 valence electrons, 1, 2, 3, 4, 5, 6. Each of it would be one hydrogen would take up and the next hydrogen would take up. Now I have 4 valence electrons, and these 4 valence electrons, they should form lone pairs. Pair means 2, 2. So 2, 2 electrons would pair up together to form lone pairs. So these 2 would form one lone pair and these 2 would form another lone pair. So which means that I will have 2 bond pairs plus 2 lone pairs. So totally it is 4 electron pairs. 4 electron pairs. Similar to ammonia, we are having 4 electron pairs but 2 lone pairs. So I can write it like this: hydrogen, hydrogen, and the lone pairs, in order to minimize repulsion, they would stay far away as far as possible. Because of repulsion, they would be as far as possible. So this is how we'll have a tetrahedral geometry but a bend shape for H2S. Now coming to the case of H2O. H2O is again, it is falling in the same sulfur also, H2 and all of them fall in the oxygen category family. So this would also have 6 valence electron. My central metal atom oxygen would have 6 valence electron. 1, 2, 3, 4, 5 and 6. Now hydrogen would take up 1, 1. Each hydrogen would share 1 electrons, and the remaining 4, they would pair up in 2, 2. So these 2 would pair up and form one lone pair. Next 2 free electrons would also pair up and form one lone pair. So totally I would be having 2 bond pairs plus 2 lone pairs, which means that I would be having 4 electron pairs. Now this structure is also very similar to the previous H2S. Its geometry is tetrahedral and shape would be bent. I'll have oxygen at the center, hydrogen and hydrogen, with a lone pair here and a lone pair here. Okay. Now coming to the last example, which is methane. So let's draw methane. Carbon would have 1, 2, 3, 4. Carbon's valence shell electrons are 4. Then the 4 hydrogen atoms they represent 1, 2, 3 and 4. 4 hydrogen atoms I represent, which means that this has 4 bond pairs and 0 lone pairs. There are no free electrons that are present, so 0 lone pairs. Totally it is 4 electron pairs, which means this would have a proper regular tetrahedral structure. Hydrogen, hydrogen, hydrogen and hydrogen. So these are the geometries and the shapes of the molecules starting from ammonia to methane. Okay. Now let's look at their bond angles. Now from the table we saw that if the bond pair without any lone pair, if we are having 4 bond pairs alone, there is no lone pair means only 4 bond pairs are there means, then that would have a bond angle. A tetrahedral structure would have a bond angle of 109 degree. Okay. So approximately this bond angle for methane is having a proper tetrahedral structure. It does not have any lone pairs. So that would have a bond angle of 109 degree. Clear? Now let's consider the case of ammonia. When you consider the case of ammonia, it is having 1 lone pair. Out of the 4 electron pairs, 1 of it is taken up by the lone pair, and because of that, lone pair bond pair repulsion would come and the bonds, that NH bonds, would come closer, and since they come closer, the bond angle would reduce slightly from 109. Proper tetrahedral structure would have 109 degree, but here because of the lone pair, the bond angle reduces slightly, and now here in this case we would have a bond angle of 107 degree. In case of ammonia, the bond angle would be 107 degree. Okay. Now coming to H2S and H2O, both of them are having 2 lone pairs. Both of them are having 2 lone pairs. So because of an extra lone pair, in ammonia it was 1 lone pair, and now in H2 and H2S it is 2 lone pairs. So which means that the bond angle would shift even further to a lower value. They would shift even further. They would come even more closer. The bonds would come because of lone pair repulsion and lone pair bond pair repulsion. So this would come, bonds would come, that SH and OH bonds would come little more closer, and bond angle would shift further lower from 107 also. It would come little more down, and now out of the two, which would have a lower value, that would, both of them are having 2 lone pairs, both of them have the same shape, both of them have the same surrounding atoms, both of them have 2 lone pairs and 2 bond pairs, everything is the same. So the only difference is the central metal atom. So in this case we have to look into the electronegativity of the central metal atom. So as the electronegativity of the central metal atom decreases, so whichever is having a lower electronegativity, the central metal atom, which of the 2 central metal atom is having a lower electronegativity, then the bond angle would be lower for that. So I can say that as electronegativity of the central metal atom, electronegativity, if it decreases, it means that my bond angle would decrease. Bond angle would decrease. I can say that as electronegativity decreases, my bond angle of the central metal atom, it is decreasing, so bond angle decreases. So out of the H2O and H2S, one has central metal atom oxygen and another has central metal atom sulfur, and sulfur has a lower electronegativity compared to oxygen. So H2S would have lower value bond angle and H2O would have a higher bond angle. And so my water molecule would have a bond angle of approximately 104.5 degree and H2S would have approximately 90 degree. Bond angle for H2S would be approximately 90 degree and for H2O it would be 104.5 degree. Highest is methane, then it's ammonia because of 1 electron, lone pair electron, then it is H2O because of 2 lone pair electrons and also higher electronegativity of the central metal atom. And finally it is H2S because of 2 lone pair electrons and the lower electronegativity value of the central metal atom. So I can give the arrange this in the increasing order to be H2S the least, then comes H2O, and then comes NH3, and finally CH4. This is the order here. So that's it for today. This is all about VSEPR theory, how we can solve the problems, predict the shapes and geometries easily using these simple steps. So hope you enjoyed this. Thank you so much.